Welcome to the FeatureScript presentation. I'm Moitri and this is Ashley. The AIDE FeatureScript team is responsible for writing the code that optimizes the geometry of the Agua Clara plant. FeatureScript writes code that automates and optimizes on-shape designs. This code is modular and it calculates plant component dimensions. FeatureScript is relatively new. We were earlier using Python to integrate with the Onshape designs. However, it integrates really well with the Onshape platform, which is why we use FeatureScript. Using FeatureScript, we can write code like this that regenerates geometry like the L form over here. So all the user has to do is to enter inputs and there's code that translates it into geometry. We can thus calculate plant dimensions and generate modular and scalable industrial infrastructure.
So this semester, we're working on two projects. The first project that our sub-team as well as other eight sub-teams are working on is three-level design. So three-level design has three components in Onshape: the hydraulic design feature, the design part studio, and the build feature. Users to create a plant or plant component from one feature. For example, a feature such as length could be used to create a box of any size. Our sub-team is also working on test functions in FeatureScript as well. And our test functions will test the hydraulic calculations that we've encoded in previous years, such as the density water program. And for example, this program should return a value of 0.001 kilograms per liter as the code demonstrates. We are also working on, as I mentioned before, we are working on the three-level design, and this is a model for one of the specific parts of the three-level design, the hydraulic design studio. So the hydraulic design studio basically takes inputs, um, puts them into hydraulic calculations, which can then be used to generate geometric outputs. So it is at the lowest level of the three-level design. And in the example we will discuss, it will take in the side length of the box wheel model using three-level design. And then next we have an example for the hydraulic design studio. So in this example, as you can see in the code, the flow rate and the height of the bottom row, as well as other features of the LFOM, are taken in as the input to the hydraulic design studio. And then we can use a function to calculate different features of the LFOM. So in real life, the hydraulic design studio contains the bulk of the functions that run hydraulic calculations like density water.
This was the lowermost level of the three-level design. Next comes the design part studio. This is an abstract view of the design part studio, which takes in matching inputs as the hydraulic design feature, which are entered in by the user. For example, input 1, input 2, input 3. This generates an HDF instance, which is geometry, and this leads to features like an extrude, fillet, or super derive. It also contains the results of all the calculations that has been run and calculated inside the hydraulic design studio. Unlike the previous level, which was the HDF, it does not only run calculations. It creates a geometric instance called the HDF and outputs features like extrudes, fillets, and super derive. This is an example of the design part studio. Here, you can clearly see that the code that has been written generates geometry that can be seen at the left side of the screen. This has been generated by the Design Part Studio that takes in an input from the Hydraulic Design Studio and creates a geometric output that can be seen in the picture. The final goal or the final level, the first level, the uppermost level, is the build feature. The build feature is a user oriented feature that can generate an abstraction of the final design. It gives a big eye view, a big hierarchical perspective of the entire part studio. The build feature takes in user inputs and generates a design part studio based on the user specifications. For example, this is an example of the feature dialog box of a build feature. The user enters in inputs over here near flow parameters, expert inputs. The user can also enter in and override JSON by clicking on the override parameters with JSON checkbox. And this translates to the beautiful geometry that you can see to the right. Next comes testing the models that we've created. First, we will discuss that what is test driven development and why is it important. Test driven development starts with designing and developing tests for very small functionality of an application. Test driven development instructs developers to write code only if an automated test has failed. This avoids duplication of code. The way this goes around is you first add a test. Note that you're not writing the code first, you're writing the test first, and then you run all the tests and see what fails. Based on the failing test, you write some code and then you again run tests to see if the test cases pass, and if not, you refactor your code. You repeat this entire process till you get code that is free of all bugs. This methodology is often used in agile development, so we decided to use this for AIDE FeatureScript this semester. Now we'll go over how we use this for AIDE FeatureScript this semester. This is how we modularize the code base. We broke up the code base into multiple feature studios based on different classes that were present in the physchem.py Python repository. For example, you can see in the picture, in the image, how we've like broken up the testing into multiple feature studios and each represents a class in the Python code base. We use the test cases in the unit test folder of the Python iWork repository for testing. Thus, we are recycling a lot of the test cases that had been used in Python earlier to make sure that our feature script code generates the same output as our Python code. Inside the Feature Studio, how do you make sure that the output of the feature script code is the same as the output of the Python code? We maintain an array of variables, like an array where like where the array contains like multiple arrays, and each of the arrays that are nested inside the variable contains a first component and a second component. And the idea is to make sure that in all the cases, in all the subarrays, the first component is the same as the second component. So 17 by 16 inch is the output generated by calling the function pipe coupling OD with the input parameter nd dot point 0.5. Also, we use debugging techniques like suppress printing. Why do we need suppress printing? Debugging using print statements can clutter up the part studio and make it hard for us to find errors. That is why we need to suppress print statements and make sure that they don't appear in the design part studio. The way this works is if the code is correct and if all the test cases pass, then there are no print statements. However, if there are test cases that don't pass, then only those are printed. In our implementation of feature script tests, only errors are printed and test cases that pass get suppressed. Finally, we monitor the design part studio. Last presentation, we had a few feature script notices that were not running. In this sprint, we managed to get over those. What does monitoring the Part Studio mean? It means running all the functions in the feature script Part Studio and see if there are any errors. If not, then all the geometry regenerates perfectly in the Design Part Studio. This semester, we made active progress from our last checkpoint, and now there are no feature script notices being generated on monitoring a part studio. We've also accomplished our goals from the last presentation that deal with testing all the functions. Feel free to ask any question and recommendations to me, Moitri Chatterjee, at mc2259 at cornell.edu, or reach out to Ashley Zhang, whose email ID is abz6 at cornell.edu. Finally, we move on to our demo, which is the fun part of a presentation. So in our demo, we have a blank, um, we have a blank part studio, and now we call the lform build feature to see how it works. We click on, we hit on lform, and then for location, we create a made connector, and the location is at the made connector, and we have geometry of the lform that is generated here using the build feature. You can control the rate of flow from this feature dialog box. You can also, and this alters the size, temperature, fraction of design flow, etc. of the model. You can also change other factors like height of the bottom row. I can set this at 0.3 instead of 0.075, and you'll see that the 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 height of the bottommost row of holes has become much larger, much taller than it was before. So we can change the configurations of the L form using our build feature. Thank you.